I want to finish up everything to do with telescopes today, and then we're going to start into our full-fledged tour of the solar system. Again, that tour starts with the rocky planets, and it starts with Earth because the further we get away from our own planet, the less we know. And it would get really boring if I spent the same amount of time on every single planet because some of these planets we've only done single flybys for, that kind of thing. So we have a lot to say about Earth. We have quite a bit to say about the Moon. A little bit more to say about Mars and Venus, and then it thins out rapidly from there. So that's the way this is going to go for the rest of the course, basically. But let's finish up telescopes. Make sure you guys don't have any questions about light first. So yeah, remind me, what's going on? What do you guys remember? What stands out? Yeah.
This is just like one small piece of what we talked about last class, but we're talking about uh spin one half
Oh, cool. Yeah.
the atoms.
Yes. Gonna come up
And
again.
instead, like it's such that my brain, like even just like trying to visualize it, I guess.
Yeah, it's pretty wild. So spin one half is a strange thing because it's assigned to the electron. But the electron is it's modeled so many different ways, and one of the ways in which it's modeled is just as like a point particle, right? Which is weird. Um, but actually, um, you know, part of the reason that the electron isn't thought by most fundamental physicists to actually orbit the atom is because that point particle would essentially have to travel faster than the speed of light, which they don't think is possible, uh, based on formalisms from relativity. But if the electron is actually the whole surface of the atom, then all of a sudden its motion, this spin one half motion included, doesn't have to violate the speed of light restraints at all, actually, because the thing isn't just flying around like a particle. It's actually just moving in place. It's a rotational velocity. So the surface itself isn't doing anything crazy. Uh, but yeah, spin one half's an interesting piece of the puzzle. And I do think it can be visualized, whether it's true or not, that it does what the way that I've illustrated it. Um, doesn't matter as much as the fact that it can be drawn in such a way. Yeah.
Have struggled with this visualization as well. And what I kind of settled on was thinking about almost like a Mobius strip.
Yeah.
Start a pen on one side and draw like go all the way around. And by the time you pull the whole thing through, there's ink on both sides.
It is kind of the way I've drawn it is Mobius-like in some sense, right? Because it involutes through the center.
Yeah.
Um, so I didn't really mention this, but like in some sense, like I should give my wife some credit with all of this too. I didn't really do this well enough last time, and I felt terrible. I actually was talking to her about it afterwards. And so my wife and I, like full disclosure, have been working on a book to visualize a lot of these fundamental features of the atom for several years now. It's almost done finally. And we've hired like a really fantastic illustrator to do some of these drawings for us. Um, but the goal of the project is really to give form to the fundamental equations of physics that define the atom and define the way that things behave, like light and electricity and magnetism. Not really like so much to as some sort of like new theory or anything, but really just to give form to the theories that already exist. So to give some sort of material shape to the equations because they don't exist right now, which is really bizarre to us. Um, so I guess what I'm trying to say is there's a fine line between saying something is so and saying that it could be so. And so this picture that I've given you guys of this involuting atom, it is consistent with all of the equations, but um, God only knows what the atom looks like because no one's ever going to be small enough to get down there and look at it exactly. So yeah, it's an interesting limit of our observational abilities, which is kind of interesting. But the fun part is that most people think spin one half can't be imagined, and I don't think that that's true. And I've tried it on a lot of people smarter than me, and seems to work at least. So what else? That was kind of fun. Spin one half's going to come up again because we got to talk about magnets again soon. So we're not done with all this atomic stuff, but we'll need to think about this a little bit more when we start thinking about how magnets work. Because one of the craziest things about this rock we're standing on right now is that it has this really protective magnetic, you know, we call it a magnetic field, but essentially it has a really, really strong magnetic presence that shields us from all sorts of nasty stuff that would probably wipe us out of existence otherwise. What else, guys? Does that make sense? First of all, are we all right? We're all on the same page. Yeah. Remind me your name again. I always forget. What is it? All right. Valeria.
Use the telescope for, so we're just learning more about refractors and reflectors. I thought all telescopes were refractors.
Yeah, they originally were.
But
It's kind of weird. Yeah, the addition of the mirror really makes things cheaper, and they don't weigh much. That's really the advantage. It also, you don't get all of that chromatic aberration stuff, which is kind of annoying, unless you're trying to make beautiful art house films. So yeah, that's kind of cool. I'm gonna talk a few more things about telescopes. There's a couple of other types of telescopes that we didn't get to, that we should at least mention before we move on. Yeah.
After last class, I still had a bit of I don't know if we talked about this and I just forgot, but about what exactly photons
Mm.
would be.
Yeah, I think we kind of ended on I think we ended a bit on the story of black body radiation, maybe, or we moved on. Actually, no, we didn't. We got into telescopes.
Mentioned that there's a good reason that we quantize
Mm, mm,
light into photons, but I don't
mm.
know the reason.
Okay, that's a great question. I'll do my best to be parsimonious about it, but it's so. I think that the real reason, the easiest way to maybe think about this is that all evidence of light is going to be electric in nature at the end of the day. So if you want to make a detector that detects light, well, you could say your eyes detect it, but your eyes are electrical in nature. They have chemical changes in your retina that are associated with having received some kick of light. If you want to make like a CMOS chip or any of these things, you you still have an electrical readout in almost every single case. And electricity is quantized, right? So this is traditionally described as the electron. And the reason that I'm suggesting to you to visualize perhaps why it is that the active surface of the atoms, the electron, is quantized is because it goes into these resonant modes of vibration that give it those surface features that make it active in the first place. And so, you remember the Chladni plate example? You can put more energy into a Chladni plate and you won't actually change it into a new resonant mode for a while, actually. They sort of snap into these configurations at some point. I think the electron's kind of like that too. And I think that you can have a fair amount of vibration going into the surface of an atom before it snaps into a new configuration. And the only way that you would have evidence of anything having ever happened is if the electron changes its state into a new energy state. That means that it snaps into a new resonant mode, basically. So I realize this might not be the most satisfying explanation, but I think you could think of it as like a thresholding type of situation. Like you might be able to drive a lot of power into an atom before it snaps into the next. Like, here's another, let me put it this way. Let's say I had like several cups of water, like 3 cups of water. And these represent, when you'll observe a photon. It has to overflow, right? And so the amount of drive, you could think of it as energy, but like the amount of excitation that I give is represented by water. So I pour water into 1 cup, and these cups are all 3 cups are at different levels of fill already, right? If I pour it into the first cup and it's already almost full, it'll kick over and that basically cross that threshold. So it overflows and we say, oh, well, there was a light signal there. Then the next atom, the next cup, it's half full, and I pour some water and nothing happens, right? Maybe I even pour the same amount of water that I did into the first one, and nothing happens. I think that they in some sense have this, Andrew almost described it as capacitance at some point. Like they can build up some degree, they have some ability to store energy to a point before they actually evidence change. That's the way I'm looking at it.
Sorry. Basically, a readout.
Yeah, well, ultimately, yeah, right. I mean,
So, because we put enough energy until it gives us an on.
yeah, yeah. I mean, I think that's a fair way to look at it. And yeah, yeah. There's another piece of this too, which is kind of interesting, and I'm not sure how this plays into it, but there's another way to look at it, which is that, um, and this relates to Planck's. Planck was the guy who quantized light originally, and he did that to solve the ultraviolet catastrophe. And it was really a mathematical trick that he did because he just found that if he put a constant into the equation, he could limit the amount of energy that came out of a given wave, essentially. And he was like, great, I solved the problem. Now the black body curve of the power spectrum matches the experiments. But he didn't know why it was there. And it really bothered him all the way to his death. And I think like another way of looking at this, and by the way, Planck's fundamental relationship is that the energy is in proportion to the frequency of the light. It really has nothing to do with how intense the light is. I wouldn't say nothing, but it primarily depends on the frequency of the light. So, X-rays are really high frequency light. They're really intense. They'll rip your DNA apart. Cell phone radiation is really low frequency, so it's not going to hurt you. It's very low energy. So, baked into that is the notion that light waves are always full waves. They're always an entire reset. So they go full positive charge, full negative charge. Let's say in the electric space. That kind of makes sense, though, and I think it'll make more sense once we get to magnetism, because, or you can just think about it in terms of what we talked about with electricity already. If the light wave only depolarized in one direction but never repolarized, I don't think it would be distinguishable from just an electric source or from a magnetic source. In other words, if you only went in one direction with the light wave, if the atom's surface wasn't doing some sort of twist and going back and forth, I think that it would just be indistinguishable from magnetism or electricity at that point. That might not be the best way of thinking about it, but it does kind of imply that light is a full wave at the same time.
Okay, so photons are just a unit measure.
There are, and there's two ways to look at that, right? There's the readout from the experimental side, which is like, why is it that we only see discrete changes in our measurement system? These, what we would call a photon. There's also the fact that light travels in full waves, and they have to be a complete depolarization and repolarization, right? They have to go full cycle to be considered light. Otherwise, you're just, if it's too short of an interval, or if it just polarizes in one direction continually, well, then you're just going to have electric or magnetic effects as a result of that. And that'll make more sense once we do magnets. So hold on to that thought and see if it still makes sense later.
We're saying light waves. We're not just talking about visible spectrum. We're talking about
Yes, sorry.
full
Yeah,
EM waves, like the spectrum.
that's right. And that's something I do that not everybody does, but I think that it's needlessly confusing to treat the electromagnetic spectrum as if it's not light, It's all the same. The mechanics are all the same. Yeah, I just think it's needlessly confusing. Usually, I think when most people most astronomers would probably just call light visible light. But yeah, atomic physicists perhaps not. So the whole EM spectrum, all the way from X-rays and gamma rays, things that'll rip you apart, all the way to radio waves.
And when you talk about light has to be a full wave, you're talking about like the S of a sign, or just it has to have those polarizations, right? To be an interval.
Yeah,
it's the C of one wave. That's only half of it, right? It has to complete.
Yeah, it's weird because it really stops making sense when it's just half of a wave or something.
Yeah.
And even in the first wave, like if you look at, so you talk to people who design antennas, there's this thing called near field versus far field effects. And the near field are really in that first like half wave or so. And basically nothing behaves as it should in that first spot. It's almost like you have to, it's almost like to really use any of these fundamental equations for light, you need a frequent behavior. Like you have to have multiple cycles for it even to make sense. And so, yeah, I think that in some sense, probably the way that I went with the threshold is probably the best way to understand it, because you have to match the right frequency to drive a particular atom, and let's say an electron, into the next energy state. If it's the wrong frequency, if you have the wrong tune playing on your Chladni plate, you're not going to get into that next excitation level. You can play slightly higher and it'll just be chaos, right? Or it's actually going to buffer the signal pretty far, so it'll stay in the first pattern on the Chladni plate as you adjust the frequency, and at some point it'll scatter and turn into the next one. I think that's really where the whole quantization of electron energy states comes down to. It's not the same up and down vibration in the electron. It's the actual ringing of this spherical bell, basically, which is a little bit different. So yeah, those details. I mean, I realize these details will probably only matter to a couple of you, but they're really important to making sense of, things that are otherwise a bit magical, like light and gravity, magnetism, electricity. These are a few of those things that, for some reason, modern physics is perfectly comfortable with keeping as somewhat magical at the moment. So that's why I really want to bring some visualization to them. All right, what else? We good? Yeah. Is it Mackenzie?
So the mirror scope is called a reflector, and then the refractor is lens, right?
Refractor and reflector. Yep. The mirror is the reflector. Yeah. Refractor. Yeah. There will not be an exam though. Don't worry about it. It's a bit weird. So anytime you have a medium that changes the let's say travel path of light or anything, it's called refraction. Yeah. Yeah. That's right.
Looking at the shell earlier today, I noticed, so I kind of got reminded that most of the terrestrial planets are closer to the sun. Do you know if that's the case, like for outside solar systems too?
There's a funny thing about other yeah, what are you gonna say?
No, it's
It's
that burned into my brain.
really interesting. Yeah, we have a weird solar system. I think there's gonna be a point, I'm pretty sure in this course, yeah. We'll compare some other solar systems to ours. We have a pretty weird one though, I will say.
It's not normal that like gas planets are not.
Well, so all of this requires like a bit of caveats, because it's really hard to see rocky planets, right? So gas planets are big, they obscure some of the light from their sun. They're much easier to see, so we're biased towards the big planets. That being said, it seems like our solar system is pretty weird. It has a bunch of different types of planets. We don't really see much of that. And the order in which they're in is kind of random compared to a lot of other solar systems. So
Possibly said that. It's just.
yeah, that's kind of where I'm at with it. I don't know how reliable all of that is, but we'll compare some of that when we get to it. What else? Anything else, guys? In last class? All right. Well, let's keep cruising. I do want to mention a couple more things. So we were talking a little bit about this spectroscopy thing last time, right? And where did I want to go with this? You can fingerprint a lot of stars. A lot of what we see in astronomy, and this is going to matter more next semester when we get away from our own solar system, but it's worth pointing out that this is pretty wild, because you can fingerprint both the temperature and the stellar atmosphere of stars, right? You can get the gases, remember, give these little lines which are overlaid because the gases absorb the light, which is coming off the surface of these stars. You get these really nice fingerprints. And so this was a huge, huge advancement when this was discovered. It was pretty much developed almost entirely between this weird amateur couple named the Drapers in New York, upstate New York, and the women at the Harvard Observatory during the First World War, when all the dudes were away fighting. So this is going to play out, more importantly, like I said, next semester, but it's pretty cool because what it means is that we can get a lot of different pictures, especially depending on which wavelength we look at these stars and these galaxies and nebula in, right? So I think this is a picture from your textbook, but if we look at different frequency spaces, right, assuming that like we just said, light is all of these frequencies, all the way from X-rays, which are really, really short, fast waves, all the way to really slow waves like radio waves. We can tune our telescopes to look at any one of these things, and we get very different pictures as a result of it, right? So let me see if I have this. I think we're basically looking at X-rays on the left. I think we're looking at visual range in the middle, and then infrared radiation on the right. So infrared's kind of interesting because it's generally taken as a readout of heat, as a way that objects radiate away heat. And you get very different pictures of the Orion constellation depending on which wavelength you're looking in. Here's another example of that. Really crazy different. This is the Crab Nebula, I believe. Let me check. You basically have completely different pictures of this thing depending on which piece you're looking at. And ideally, this is beyond the scope of the discussion today, but ideally by studying each one of these pieces, you can start to reconstruct a story for what these things mean. And we'll be talking about the Crab Nebula as it relates to novae and things like that next semester, but that's outside of the scope of today. All right, so radio astronomy is another one we didn't really touch on, although I feel like I've talked about it already with Carl Jansky, and we talked about the sidereal day versus the solar day, and basically how this dude discovered radio astronomy. He was working on he was working on communications stuff at the time. And so radio astronomy is interesting. So that was basically the moment when people started thinking, wait a second, I think we can look at other wavelengths besides visual light to make sense of things. And so that was a pretty cool moment. I'm not going to get too much into the weeds about that. We already talked about his discovery. Another thing that's really interesting about radio telescopes is, and here's some pictures of radio telescopes. Don't worry about what this is just yet. We'll do that next semester. What's kind of cool is sometimes these radio telescopes, since radio waves are so big, it's really hard to pinpoint objects in the sky with them. I'm trying to think of a good example of how this works. So if you want to see something that's, let's say you're using a microscope and you're looking at something, do you want to use a light that's really big waves or little waves to look at something under a microscope? Like, which one's going to give you the best resolution?
Probably the smaller waves.
Yeah, the smaller waves, right? Now, we sort of had a similar problem when it comes to radio telescopes as well, because radio telescopes have these huge wavelengths. It's actually very difficult to pinpoint anything with them. So what they do is they make these huge arrays where they'll scatter these telescopes all across the globe, and they'll basically look at the sort of difference in the phase as the radio light, comes from, say, the center of a galaxy somewhere, and how it gets out of phase with one that's far away. And they'll basically be able to set up some sort of interference system where they can tighten down the resolution of these radio antenna. In other words, they're basically making a big antenna by setting up lots of little ones across the globe, which is really cool. And I think radio telescopes are the only ones you can get away with that kind of thing with. So you can set up enormous, they call them arrays, essentially. Now, the single dishes might give you better sensitivity to like an individual change in intensity of a light or something if you're looking at how something's pulsating, but you get this really nice angular resolution, so actual visual resolution as a result of these arrays. That's pretty cool. All right, and then the final frontier is putting these telescopes in space, right? Because our atmosphere is a nightmare for telescopes. And you could go to the desert, you could go to a mountain, and at the end of the day, best place to take a picture of stuff in space is from space. So I think this is a picture from Hubble. We have a new one up there called the James Webb Telescope, I believe it's called. They keep changing the name. He got canceled for some reason. I think they're just calling it JWST or something now. But anyways, we have a better version of this. And, the Hubble, of course, was able to see 13 billion light years with resolution. The James Webb, JWST, got almost another billion years out of that. So that's cool. What else do I want to say about this? You can actually set up X-ray telescopes too in space. X-ray telescopes, a little trickier on Earth because our atmosphere saves us from most of the X-rays, which is really nice. X-ray telescopes are weird though, because you might ask, how would you take a picture of an X-ray? They go, right through things, right? They're relayed straight through most objects. That's why you can go to the doctor and they'll take an X-ray of your foot or something if you break your toe or something, right? So how do they do this? It's kind of cool. They actually take advantage of the fact that you can reflect X-rays, but you can only do it at really shallow angles. It's kind of like skipping a stone off of a pond. There's this feature called total internal reflection, and you basically set up a bunch of narrowing mirrors at increasing angles. And so I think it's like a couple of degrees. What is it? 2.4 degrees is you have to have the angle of the incidence of the X-ray under 2.4 degrees, and it'll be scattered off the surface like this. And so you kind of focus all of these X-rays in by narrowing and narrowing your series of mirrors to a point where you can make a little X-ray picture like the doctor does. So that's pretty rad. And what else do I want to say about telescopes? Make sure we covered everything we need to. I mean, one of the biggest problems with getting telescopes into space is they're big and heavy and they break. The Hubble got broken at some point. So I think a huge piece of the puzzle going forward is going to be figuring out how to make telescopes that fold up and deploy, right? It's kind of cool how they are thinking about getting things into space like this, because they're modeling a lot of it on the way that plants operate, right? When they unfold, like pine cones and things like this, right? This kind of origami-like structure where you have small pieces that unfold naturally once they're into that environment. I think this is the biggest trick, because you can't have these big heavy chunks of things that are going to sag and break, and they're difficult to get up through the atmosphere. I mean, the hardest part about getting into space is the atmosphere. That's why all of our rockets are these like hot dog shaped things, because they're trying to punch through the atmosphere. If you're on the moon, there's less gravity on the moon, but if you're on the moon, there's no atmosphere. So getting stuff into orbit on the moon is super easy. You basically just throw it upwards really hard, put a couple boosters underneath your pallet. You could have a big, wide, it could be the size of a football field for all it matters. There's no air resistance on the moon, so you can just kind of shove things up into orbit. The Earth is really difficult because the atmosphere restricts our motions. So any telescopes that we build have to be folded down to fit inside of the hot dog thing and get rocketed up and cut through the atmosphere. All right. So I think that's where I want to put a pin in it for telescopes. Questions, thoughts, concerns, telescopes before we move on? Sarah, yeah.
X-ray.
Oh yeah, sure. Well, to the best of my ability, I'm no expert on this. I just thought it was kind of a cool, uh, a cool mechanism here. So the basic idea is that it is true that if you take an X-ray and you shine it on an ordinary mirror, it will just penetrate straight through the mirror. I think it's probably more rational to say it would just that light signal will be relayed directly past the mirror onto whatever's behind it. But and I haven't given a lot of thought to the mechanism of why this works out. So I'm sorry that I don't have the exact answer for you, but there's something about when you send that signal at a very, very low angle, right? So you basically shine that ray at a really low angle where it basically gets relayed on forward. It doesn't penetrate through the material. And so they basically set up an increasingly, this only has 2 of them shown, but I think that there's many, many series of these low angle plates where they'll just, instead of using a traditional lens to focus the light like you would with a refracting telescope, for instance, the X-ray would just kind of go straight through that, for lack of a better way of putting it, and you wouldn't be able to focus it. So the way that they focus these X-rays is with a series of these low inclined mirrors, basically.
There's a demonstration I've seen a few times with a laser underwater,
Hmm.
where if it's at a shallow angle, it will fully reflect off the surface.
Yeah,
And then as you steepen out the angle, eventually it will be
that's
like
right.
80% punching through and 20% reflecting from 100% reflection over just a tiny change in angle.
Yeah, it's a more generalized principle called total internal reflection. And I think that angle is different for different wavelengths. I don't know a ton about this, unfortunately. I do know that they have to make those mirrors out of super weird materials like gold and iridium and platinum and stuff like that. I'm sure I could waste a weekend trying to get to the bottom of what it is about this system. But yeah, total internal reflection is the thing. That's a good point. You can see it on the surfaces of waters. Um, and of course it is a thing, right? We all know that like water, you can see through it, at least clear water that's not murky. But then if you go off to the side, right, it's actually going to reflect a bit. You're going to get that what do they call it? Like that specular effect that um well, yeah, it'll basically reflect into your eyeballs, right? That's why people use polarizing sunglasses and stuff when they're out in the ocean. Polarizers are that's a huge story though. We'll have to get into that some other day. What else? Any other questions? Thoughts? Yeah.
Because, like X-ray, right now, infrared.
So if we want to think about it as a continuum, like X-rays are the kind of the fastest ones, right? Visible is kind of like medium. Infrared's a little bit longer. And then out here, we're getting into, by the way, infrared, microwave, very close to each other. And then we get out into the radio wavelength at some point.
What about
Gamma rays, even smaller down here. Gamma ray telescopes? That's a good question. I don't know. Somebody want to Google that? There must be gamma ray telescopes.
Don't they have like the depictions? What it would look like with the game is like those just kind of slated, I guess. Then
Yeah, we get into these are good questions. Yeah, there's gamma ray. Are they similar to the X-ray telescopes in build?
One that I don't
Is it a space telescope or an
know. Yeah, it's
Earth-based?
a satellite. The Fermi Gamma Ray Space Telescope. Formerly called the Gamma Ray Large Area Space Telescope.
Interesting. All right, I'm gonna put a note for next year. Well, have to look this up. Um, you know, gamma rays. Yeah, so the focusing is the really tricky part, from what I can gather. You can have detectors that'll pick these things up, right? Um, the focusing gamma rays sounds like it'd be even harder than focusing X-rays, but I imagine it's a similar endeavor.
It's only detects bursts.
Oh, okay. So it's just like this happened or this didn't happen kind of thing.
Yeah.
Yeah. Well, so this kind of really, really high energy radiation is quite, I don't want to say, let's just say it's quite rare. Um, it takes really, really high energy processes for this to happen, trying to think of something that's, uh, like a crazy solar flare or something like that, where you just have a tremendous amount of material colliding with another, with itself or whatever. Something really, really high energy would give you gamma ray bursts. So not the most normal way to look at, say, a planet or a star or something like that. All right, what else before we get into these terrestrials? Yeah.
If the speed of light is constant, how do the waves have different uh energy like scales? How do the waves get bigger and smaller if it's not speed?
Yeah, it's a good question. So the constant speed of light really refers to the propagation speed. These are transverse waves, which really just refers to how fast the electrons at either end are oscillating in their state, right?
Oh, okay, that makes sense.
Okay. So you can oscillate in your state really, really fast, but the wavefront itself is going to propagate longitudinally at a constant speed, right?
Good.
It is a little bit hard to think of because light waves are, in some sense, I think this is why they've given people so much trouble over the years, is that there's not a great analog in our world for that. Like the surface of a pond is a transverse wave. You see these little ripples emanating out, and the thing is going up and down, and the wavefront moves outward. And sound waves are longitudinal because they propagate this way and they wave in this direction too, in the way in which they go. Light waves are kind of a little bit of both. They oscillate in this transverse fashion, which is just the electric component or the electromagnetic component. They also propagate longitudinally, which is annoying, and the wave front propagates longitudinally, so it moves outward. But there's no compression like sound. Um, yeah.
Sound might still be a good analogy just from the difference of frequency, amplitude, but travel time remains the same generally. Like the pitch of the sound can change and the volume of the sound can change, but it'll still take the same amount of time to get from the speaker.
Yeah, or like a wave in any material is going to be the same thing. As long as the material is constant, you're going to have a constant speed in a material, in any material. That's true.
Material properties of sound pretty similar.
Yeah. Yeah, it sounds a decent analog. It gets weird when you start like talking about gases versus, yeah, it starts to fall apart. But sound in a material, I think, is the most right way to think about it. And ultimately, I think that it's rational to assume, I know this isn't like a popular way of looking at it, but I think it's rational to assume that some material is conveying light from one source to another, even if we don't understand the properties of that or its structure exactly just yet. So yeah, it is some sort of deformation. Sound is weird though, because sound is like these compression waves, right? And light isn't quite like that. When we talk about it, I think there is some compression happening, but that's not what's waving exactly, if that makes sense. It's really the polarity at either end that's waving.
So just to clarify what you're saying, because there's no compression, if you had, say, visible light, if you think about it as a sound wave in like a minute audio file,
Okay.
and then you add energy to turn it into an X-ray, you'd have the same number of waves. It would be a longer file. It'd be a longer duration.
You could think of it that way, but yeah, it's weird though. I mean, yeah, the compression thing is weird. So it's like, yeah, this is. I'm not sure about that example. I don't totally follow it. I would say that generally when analogies are made between sound and light, there's a frequency space for each, right? So high frequency light is just like high frequency sound waves in that analogy. I think analogies are scary because they almost always screw you over in the end. So we have to be really careful with analogies. But if you think about what's waving in a sound wave, maybe that's a good place to start. Like, what is waving? It's just density. It's literally density versus time, right? So there's places where there's more density and less density. I can walk into a wave of more or less density and I experience a higher frequency. I walk away from it, I would experience less of that, right? This is Doppler shifting. If I stand still, I'm going to get hit with the wave front as it moves at a constant speed, right? Depending on the medium. If it's in air, then the air is the same temperature and blah, 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 blah. All this is held constant. Then I'm going to get hit with waves of high density and low density air, right? Compressed air versus rarefied air. Light's weird because what's waving in light doesn't have anything to do with density or rarefication. It's just the polarization of your antenna at either end, right? So if I'm sitting here and let's treat my eyeballs as antennas right now, right? The frequency with which the antennas in my eyes are getting smashed with this light from the ceiling, that's determining the wave speed. Not the front of the wave, not how fast it takes for me to receive the signal, but it's giving me the frequency and the wavelength information. Because what's oscillating is the electric state. It's not anything to do with the compaction of anything along the way, basically.
Okay.
I'm sorry, yeah, that's
No, it's okay.
it's the best I can do.
The duration of the sound is the same, you just end up with more peaks,
Yeah,
right?
yeah, yeah.
So there's a visual compression, but you end up with it's like the same.
Which, like, I think it's not too far. The sounding is like a little bit, it can get you in the weeds a little bit, but I mean, assuming that there is a medium conveying light, it is probably being deformed more often if it's a high frequency light than if it's a low frequency light. Like, there's more deformations per unit time. But I'm not sure how that relates to the change in density of that medium or anything like that. I doubt it does, to be honest with you. Actually, Newton, was it Newton? I believe it was Newton really, really wanted to explain light. Once he discovered there's different colors inside of white light, he used this prism. He really wanted to describe it in terms of how he understood sound in this way, right? In terms of density changes in the ether and stuff like that. But it turns out to not really work out that way at all. How do we know it doesn't work out that way? Like, people thought originally, well, light should go slower in a denser medium, right? So they got denser versions of, I don't know, like something like glass or something, right? Because it does appear that light goes slower inside of glass. It doesn't really, but it appears that it does, compared to air, for instance, right? But the more they investigated this, the more they found that it actually had nothing to do with the mass density whatsoever of the medium. So they prepared some different solutions that had more or less density, and they found really no correlation. So that whole analogy to sound kind of fell apart pretty quickly. This was like maybe in the 1800s or something by the time this was happening. Unfortunately, it was kind of a disaster for the subsequent generations, because instead of recognizing that it had nothing to do with density, they actually just termed how much light gets bent in a medium as optical density. It has nothing to do with density. They just call refractive index optical density because that's how people in the 1700s were thinking about it or something. So they still call how much a medium bends light or slows down its wavefront apparent motion optical density, but it has nothing to do with density whatsoever. Which is really crazy. And I see like pretty high level physicists make this mistake all the time. And it's really, really hard to talk them out of it, but it is true. All right. Light? Anything? No, we can talk about light for the rest of the semester. It's fine. But we should probably kick off our tour, because yeah, we have the whole solar system with the planets to make our way through. And the one that we're standing on, it turns out to be one of the best ones to learn things about as we go. And I think the one that we're standing on probably, has the best hope of giving us an idea of how these things happen? Like, that's a question I'd really like to wrap this course down on for the last week or so, is how did the solar system come to be the way that it is? And you might have got some previews of the standard story already in your textbook and workshop assignments. You know, the basic idea is that there's this swirling puddle of gas or whatever, and the star, you know, condenses. Well, they wouldn't use that word condense. It gravitationally collapses out of this gas pile, and then the planets kind of do the same thing. It's a really, really woefully inadequate story, though, the closer that you scrutinize it. And I think we're going to see that story fall apart as we start looking at each one of these planets. But I think that the Earth gives us kind of the best hope of being able to actually rationalize where these planets do come from. And so that's why it's probably worth sinking into these geological and structural features of the Earth for a few days, because we have the most data about this place of any one of these planets. We've been to a few of them. We've had some robotic landers on a few of the surfaces of these things, but just not a ton of information about other stuff. So the Earth is a great test bed. And you know, the Earth is actually it's a terrestrial. So we have this category of rocky, dense bodies in the solar system. And I got a picture of them up here. So we have, see here, we got Mercury over there, closest to the sun. Venus, next closest. Us, our moon, and Mars. And then sometimes Vesta and some of the roundish asteroids are considered rocky planets. Depends who you talk to, because technically those asteroids are also orbiting the sun. They don't have their own moons, and so they're technically planets. They're like planetoid, little sub-dwarf planets. We'll deal with the asteroid belt when we get to it. But
So we're not gonna get to
I mean, what can we say about Pluto? May as well do it right now. It's there. There's a bunch of them sort of like it seems like. Yeah, we'll get to Pluto. We'll get to Pluto. But almost anybody else is more interesting because we have much more to say. Poor Pluto. Yeah. So these are the guys we'll be dealing with for the next few classes. But the one that we're on right now, I think, is the one we can say the most about. Now, they're all kind of interesting because they're super dense compared to everybody else for the most part. They're all made of rocks and metals, which is really interesting. And we hope to be able to relate them to one another, although that might be more challenging than it looks on its surface. Venus especially is really similar in size to us, quite similar in density to us. But there's problems. You know, Venus is very, very different. It doesn't have liquid water. It basically doesn't turn. It almost doesn't turn. It takes, you know, I think it takes some like 200 something days for it to turn, but it's basically orbiting the sun at a similar speed. So its day and its year are on par with each other. It's a very, very strange planet to compare ourselves to. It's got a really thick atmosphere too. Not as thick as some of the gas giants or the ice giants who have enormous atmospheres. But yeah, it's really thick. And it's a strange planet compared to ours in many ways.
and Terrestrial is really funny because it's just
Earth. Yeah, Terra. What is that? Is it Latin? I think it's Latin for Earth, yeah. You also, yeah. What's the other one? Telluric. Telluric also means Earth. There's like two in Latin. What else can we say about these things? I mean, their densities are actually all quite high, which is quite interesting. The Earth, as I pointed out in like the first class or so, is the most dense of all of them. Now, one feature that I pulled this actually this afternoon, this chart off of Wikipedia, because I thought it was quite interesting that it has this other column, which is called uncompressed density, which I think is quite interesting. You might be like, all right, well, the mean density is fine. This is the one that's in your textbook. You know, you can order these things. Mercury is really dense, Earth's really dense, Venus is really dense. Everybody else kind of goes down from there. But what is uncompressed density? That's a really weird category to just stumble across. What do they mean by that? Yeah,
I'm talking about the atmosphere.
I thought so too at first, but no. What they're basically saying is that if you were to like take the rock out, or the rock and metal out of the center of the earth or something and put it in the vacuum of space, it would expand. Right? And so they're like, if the material of Earth had expanded to its full capacity, its final density would only be 4.4 grams per cubic centimeter. Which is really weird that some of them are decompressed and some of them are not decompressed. And I actually think this is a really fascinating feature that I'm going to build out more for you as we go forward, because I do think that there's some evidence that these planets have decompressed since they're are in that various planets are in various stages of decompression, which might help us understand what the heck a planet is and where it comes from. And I think that's really, really interesting. Okay. What else do I want to say? All right, we're going to get into each one of these in detail. They all kind of have this basic layout where there's thought to be some sort of molten interior. There's some sort of crust layer. Different ones of these have different degrees of, what would we say, differentiation between these layers. The Earth, of course, being the most interesting in that capacity, because the Earth is thought to have this molten, perhaps a core that's solid in some sense, that's floating in a molten bath, and the core is kind of spinning separately. We don't really think that's happening to anybody else in these terrestrials, right? And why do they think that? Well, it has to do with the way that magnets work and the fact that we have this really giant magnetic field that's protecting us from all sorts of nasty stuff. So I wanted to just say that this is the most obvious difference between Venus and Earth. And why doesn't Venus have an internal magnet? It's something we can revisit as we go ahead. We have to still understand what a magnet is, first of all, how the Earth generates its magnetic field, second of all. And then we have to think about whether those circumstances apply to Venus. So we'll come back to this question, but I do think that it's one of the most interesting differences between Venus and Earth. And perhaps, if Venus had a nice magnetic field, perhaps it wouldn't look like the kind of sulfurous hellscape that it does look like. I don't know, maybe it would, but it seems like we've got something really special going on here, in addition to everything that's obviously special, like this beautiful landscape and all this wonderful oxygen and life forms. I mean, it's a very, very strange and special place. But I think that magnetic field plays into the picture for a while, if that's so possible. All right, so we'll come back to that. Let's talk about our planet for a second. So this thing is mostly made out of iron and silicon and oxygen, basically rocks, right? The things that you would associate with how you would make a rock. Now, it's also, in addition to having this really nice protective bubble around it, which we'll give its full detail to next class, it's also sitting in the perfect spot in the solar system, right? Well, what's so perfect about it?
They call it the Goldilocks zone because
Yeah.
it's not too hot, not too cold.
Yeah,
It's just right for life to exist.
yeah. What were you gonna say?
That's the same.
Yeah, what is that? What makes it just right for life to exist? Yeah.
It's to have different water. Reserves.
Yeah, that's pretty much the big one, as far as I can tell. Liquid water. It's hard to find liquid water continually on any other planet for the most part. There's a little bit of evidence of some drippy stuff on Mars. It's not super convincing and it's seasonal. What are you gonna say? Is it?
There's also Jupiter, which is kind of there's some asteroids.
Oh yeah, no, that opens. Yeah, so the question is like, why are we so lucky as to have this place? And you're right, Jupiter's what do they call it? Like a catcher's mitt or something. It gobbles up asteroids for sure. And when we look at Jupiter, you'll see it's just dragging all these asteroids around with it, both in front and behind it at these Lagrange points. It's just trapping and snacking up on all the asteroids, which is really nice. Comets too, that get too close. The last time we got punched with a really gnarly impact body, something like 100 kilometers wide, was the dinosaur ending impact, right? We'll talk about that down the road a little bit, but that was bad. It might have been geologically bad too, from where I'm sitting. It might have really, really changed the way the Earth looked in a way that, that we haven't seen any kind of changes like since then. Now, remember, the Earth was a very different place back in the dinosaurs too, right? So these impacts can really rewrite history. If you get hit with too many things too fast, you might not get a chance to have life at all. Or it might just get wiped out really, really fast. All right. Another thing that's kind of funny is basically everything is defined astronomically based on Earth, which I guess that kind of makes sense. So, for instance, Earth is how far away from the sun? Well, it's 1 astronomical unit away from the sun, right? How much atmospheric pressure do we have? 1 bar, right? Or 1 atmosphere or something, right? How much? There's another one that's funny. The period obviously is the year. We'll define other bodies' periods, their orbits, in terms of the year as well. So everything is kind of standardized based on us. Not super surprising, but we are at the center of our own story, like it or not. All right. So in terms of the organization of this thing, you might be wondering, how in the world do they know this? Like, why do people think that the course or the interior of the Earth is set up this way? Any guesses, ideas? It's actually,
Propagation.
yeah, that's spot on. That's exactly right. I mean, that's at least where the origin story for this comes. There's actually this Danish geophysicist named Inge Lehmann who made this discovery by analyzing seismic waves as they basically were picked up by seismic stations on different parts of the globe. This is just really, really fits into our discussion of wave speeds and materials too, right? We've been talking about this, like what dictates the wave speeds in a material. I'm going to be super impressed if any of you remember this, but what dictates wave speed in a material?
Constant prices.
Okay, that's a huge part of it. Well, there's 2 main factors that dictate wave speed in a material. You're kind of you kind of intuit it, but I think there's a better way of putting it. Yeah. That's one of them, density, and what's the other one?
Definition of material.
Yep, which is called stiffness, rigidity, exactly. So stiff, yeah, it's really, I mean, there's a lot of words for stiffness in physics. Rigidity is a good one. Elastic modulus is the same idea. Generally speaking, stiffness and elastic modulus are the deciding factor. They factor in much more heavily. I think mainly because density isn't that different amongst materials as much as you would think. So it doesn't get as big of a vote for the most part, but they're both important in the wave speed equation. And so what they're really seeing is changes in the rigidity of the Earth as a result of the way that these waves are kind of deflected or travel at different speeds. They actually call it refraction, which is really funny. Which again confuses the concept of refraction because the density does matter with wave speed refraction inside of materials. It actually does depend in some sense on density. That is not the case with light though. And so people get these confused endlessly. I've probably made it worse by even mentioning it to you guys. So yes, this brilliant Danish geophysicist figured this out, and they've essentially been using some form of this ever since to map the different substructures of the Earth. So we have this idea that there's a few different layers of the Earth, which is really quite fascinating. It's going to go into our bigger story of this magnetic defense thing that we've got going on, which I just can't overstate enough. I mean, our magnet, our geomagnetic influence is so strong compared to the size of our body. Jupiter has a really strong magnetic field too, but Jupiter is like, huge compared to the Earth. I don't have like the number off the top of my head, but it's enormous, enormous compared to the Earth. So it makes sense that it would have a pretty big magnetic field. The Earth's tiny and it has a really, really strong magnetic field. And so the stratification, the changes, the motions of these independent layers, their magnetic properties, their conductive properties are all going to play into how the Earth does that magic trick that keeps us alive, basically, and keeps our atmosphere from blowing away. All right. So what else do we want to say about the? All right. So if we work our way from the outside to the inside, I think this might be maybe we can hope to make it through the crust today, basically, because we have a really strange crust. So there's oceanic crust and there is the continental crust, and the continental crust is, you know, basically where the continents are at. It also tends to be it's comprised of a different type of rock than the oceanic crust, right? It's a much stranger rock. For the most part, we call it granite. And granite is a very strange rock in terms of the way that it's formed. If you want to find granite forming nowadays, it seems like you have to involve water and magma in this particular reaction. It's very, very strange rock.
Crystals.
What is it?
A lot of crystals.
Yeah, it's a very particular rock. You guys have probably seen it before. Anybody been to Yosemite? Yeah, it's all granite there. It's also one of the worst types of rocks to climb on, in my opinion. It's so slippery and smooth. Somebody said in their intro video that they were getting into rock climbing. Who was that? Maybe was it you? I think maybe it was Ezra who just stepped out. I love rock climbing, but Yosemite granite is every bit as hard as everybody says that it is. It is super slick, and you can stick your hands in the cracks, but it's got almost no features on it. So that's the continental crust. So the fact that there is continental crust at all versus oceanic is really quite interesting. I think it doesn't quite get enough play in terms of understanding what the heck is going on with our planet. So a big portion of the Earth is covered in oceans. And then we have these weird continent things, and nobody else seems to have that. So a large part of the crust and the oceanic basalt and all of that, the oceanic crust is made of this stuff called basalt, which is basically just, thawed, or what would we say? It's basically lava that's solidified, right? It's cooled for the most part. So the ocean floors, a good portion of the crust in general, overlying the granite foundations of the continents as well. There's also a bit of other kinds of rocks you guys are familiar with too. They're worth mentioning. This kind of sedimentary stuff. Yeah.
I think it might be important to mention the difference between magma and lava.
Oh, do it. Tell me.
Lava
just no. Tell me. What's the difference?
Magma's in the core.
Oh,
Lava's not.
magma. So lava is on the surface, basically. I see. Magma is before it comes out. Yeah. Good correction. All right. So that molten rock stuff, when it cools, makes up the basaltic foundations that we see a lot everywhere. There's also this sedimentary stuff. There's also another type of rock that's kind of weird, which is this metamorphic stuff, which I guess has just been reworked. So it's like you have sedimentary or igneous, this igneous basaltic stuff that gets somehow sucked down underneath and shaped and twisted and spit back out on the surface. I actually understand this one the least, but there are these three types of rock. And
tectonics.
So it's some sort of geologic process that's twisted this thing apart. We're going to get to plate tectonics in a second. And there's also another type of rock that is generally not found in abundance in the crust, which is called, they call this primitive rock or primary rock. This is interesting because primitive and primary rock is thought to have come from the early moments of the solar system, which is supposed to have condensed out of this same swirling, nebula type thing. And we would only find this kind of thing from, say, asteroids or something that are supposed to have been around since those very early moments. Yeah.
One of my favorite fun facts is before humans learned how to process ore into metal, all iron that was ever utilized was from meteorites.
That is true, yeah.
Because that was the only place we could get pure iron that wasn't ore.
Yeah, that is an interesting fact. I've heard that before too. So like there's some Egyptian iron artifacts, like ancient Egyptian artifacts, like I think like a dagger or some things like that, and they're all made out of meteors, basically, right? Because it wasn't it's not believed that these people had access to the smelting capabilities to make iron at that point in time. There's something weird though about iron though too, like it doesn't last very long in the environment, which is also troubling. So I'm like, if people had it, 20,000 years ago, would we see any pieces of it? I honestly don't know. I mean, huge chunks of meteoric iron, perhaps, but like thin sheet metal and stuff like that, I don't know.
Unless it's covered by sediment, probably.
Yeah, if it was preserved in some like bog or something nice, maybe. Anyways, there doesn't seem to be any evidence of that, so not a thing, probably. All right, so let's talk about this. I think this is probably a good discussion to close down the crust stuff on, which is this whole. I don't want to talk about the mantle right now or any of that other stuff, but I do want to talk about plate tectonics. Yeah. So this story, you guys have been beat to death with this story since you were kids, I'm sure. And so you probably don't need me to tell you the story one more time, but I will tell you a different story that's quite interesting as well. So plate tectonics was actually developed by a guy who was seated squarely outside the discipline that he was not a geologist. And this guy's name was Wegener, by the way. And people had this basic realization. They realized that fossils and mountain bands were continuous across the continents. And so Wegener basically wanted to argue that essentially at some points the continents had all been kind of jammed together and that they had moved apart over the intervening millions and millions of years, right? So that's an interesting proposal because this is pretty weird, right? Why would you find this lizard fossil down on the tip of South America only and in the tip of South Africa? Same with these other lizards or whatever the heck, these plants and stuff. It's pretty weird. The problem was Wegener didn't have a mechanism for what could cause this to move apart. Yeah.
He discovered plate tectonics, proposed continental drift,
Right.
and he didn't have the process what we now call plate tectonics to actually
Nice. That's a good way of putting it. Yeah.
how these continents drifted.
Yeah. I like that.
On a flag and going, you stupid weatherman, continents don't float like clouds.
Yeah. He was really abused, right? He got the whole Graham Hancock treatment in his day. Now there was another man named Carey at the time who also had a proposal for how this happened. I'll get to Carey's proposal in a second. But needless to say, Wegener was kind of abused pretty heavily in his day, and he didn't have a mechanism for it. And so the mechanism that you're referring to is plate tectonics, which is this idea that there is a motive force. In other words, there's some churning liquid, magma, in this asthenosphere layer that's actually kind of conveying like a conveyor belt. It's kind of churning in these convection cells and moving the continents apart, moving them around the globe. So as soon as this mechanism, and so anyways, Wegener had his idea sitting out there for many, many years. I'm actually not sure if he got to see his idea accepted before he died. He never did. That's so sad.
A couple of decades after his death for plate tectonics, I believe.
Okay. So this idea, and I think people started discovering what they now call these subduction zones eventually too. And people jumped on board with the continental drift idea. Again, they really did need to explain this, to be fair. Like they really did need to explain this, which is really bizarre and interesting. So they basically chopped the world up into these plates. And the basic idea, of course, is that some of these plates, they're being pulled around on these convection cells, right? You guys know what I mean by convection, by the way? Yeah, yeah.
Okay.
Yeah, I mean, that's exactly right. But just to clarify, when things heat up, like material, it expands, right? And because the Earth's gravity is kind of pushing things down, right? And we can deal with that separately. But you have basically this rising, right, of these pieces as they expand and take up more space, right? So you have this churning kind of cycle, things rising up, and they make these cells, right? That's the idea, anyways. That's the idea. Okay. And this is supported in many ways because we do see these actual plates. We see rips in the surface. We see, was that a nice map? We do see these places. We can actually track the motion of these plates, right, with different GPS systems. You can actually see the plates moving. Now, the closer you look at this, though, it gets a little more disturbing because the plates aren't exactly moving the way that you would expect them to be moving. North American one's kind of moving down. There's pieces of it that are moving this way and pieces of it that are moving that way. It's very strange, right? And so there was this other guy at the time of Wagner, and I'm going to come back to this piece in just a second. This is, sorry, I should have showed you this earlier. This is the basic idea that there's this magma rising up. It creates these kind of conveyor belt things which drag the crust around. The problem is that they've never actually been able to find these things. It's very strange. There doesn't appear to be actual convection cells underneath the Earth at all. In fact, where you see and I wish I'd put this picture in for you guys. Oh, maybe this is it. The places where you actually see magma welling up and bubbling have no correspondence to the actual fractures in the Earth. So you don't actually see these cells rising up underneath where these crust fractures are, which is really disturbing in terms of the plate tectonics mechanism.
Fire.
Here they are. Oops. So, sorry. So this is basically, picking at this to play again. This is basically where all of the mantle plumes are, and they have no correspondence whatsoever to the rifts or the places where we should be expecting this sort of seafloor spreading, where we should be expecting these continents to be being pushed around on their convection cells. So it's weird because on one hand, we know that the continents must have been continuous at some point. On the other hand, the direction that the plates are moving doesn't really correspond in any meaningful way towards being traced back to any sort of Pangea in the way that the continental drift theorists propose that it should. Furthermore, there doesn't appear to be actual convection cells underneath the crust. Furthermore, the actual mantle upwelling doesn't seem to be corresponding to the rips in the crust whatsoever, which is really weird, right? So what's happening? So there's this other dude that I wanted to introduce you to. Again, this is kind of the basic idea that you would have these little cells. There was another guy who was competing actually against, he didn't even know it because his ideas were also, this guy was also thought of as a lunatic, just the same as Wagner. His name was Carey. And Carey proposed a different explanation for why the continents were continuous back in the early epics of the Earth. And Carey's idea was actually that if the Earth was a lot smaller a few 100 million years ago, that all of the continents would basically zip up perfectly like little puzzle pieces. They would all fit together perfectly. And you would actually get them to fit better than if you tried to put them on one side of a Pangea globe instead. Now, Carey's idea that the Earth had basically expanded over the past 200 million years or so, he had no mechanism for that either. And I think this is the reason why both of these guys were in trouble in their lifetimes, was they didn't know what would cause the phenomenon that they're reporting. Wegener had no idea what in the world would move his Pangea all around the world. Carey had no idea what on earth would cause the Earth to expand. Neither one of them had any possible idea for what could cause that. So I will I have 5 minutes left here. I'll leave you with I want to kind of send you home to think about these two paradoxes, but I'll leave you with one more piece of the puzzle. So there's actually an astronaut that I'm friends with, and I've had him on the podcast a couple of times. Maybe we've only had him on once, actually. Anyways, he did his PhD dissertation. His name's Don Petit. He did his PhD dissertation up at what is it? What's the one in Portland? Oregon? University of Oregon? Is that the one in Portland? Portland State?
Yeah, University of Oregon.
I think he was in Eugene. He did his PhD dissertation there with this guy named Octavio Levenspiel. That was his advisor. And they were trying to make sense of something called the flight paradox in flying dinosaurs. You guys ever hear about this kind of thing? So there's these weird dinosaurs. They're not really technically dinosaurs, but they're huge dinosaur-like birds. They're called Quetzalcoatli. They're really, really weird because they're these huge bird things, but they got these pretty shrimpy wings, actually. Still big wings. They're like the size of the 737 or something like that. But when you put all animals, and really even all flying objects, on a map, basically based on how big their wings are versus how much mass they have, you can basically put all of these things on a line, right? But these Quetzalcoatli like don't fit on it. They basically seem like they shouldn't have been able to fly, which is weird because it's like, why do you have wings the size of a jumbo jet if you can't fly? In other words, if you would have dropped these things off in our atmosphere today and shoved them off of a cliff, they wouldn't have been able to fly. They might have like flying. So the mainstream archaeological explanation is they were kind of like flying squirrels. Like they would like kind of just, I don't know, they would just glide places or something, but they couldn't fly. That's the bottom line. Anyways, Don and Octavio had a different idea. They reasoned that if the Earth was different in the era of the dinosaurs 65 million years ago, in one particular way, that these Quetzalcoatli could actually fly. What do you think they changed about the Earth? That's right, not the gravity, but the atmosphere. They said if the atmosphere was only about 3 times thicker back then, if we had maybe 3 times as much atmosphere back then as we do today, these dinosaurs would be able to fly. Furthermore, what happens when you thicken up the atmosphere?
Gets hotter.
Restless.
Amongst other things, another thing that happens is it becomes more buoyant, right? So things like the effective weight. It'd be like it'd be like when we go into water, right? You feel like you're floating a little bit, right? Because it's really, really dense. The same thing would be true in a really thick atmosphere on the Earth as well, is that the big animals wouldn't feel as heavy because there'd be upward buoyancy of the thick air holding them up a little bit, right? So he thought that was a really, really good explanation for how the heck the dinosaurs were so big, because plenty of people today have pointed out that the dinosaurs were so enormous that if you tried to walk one down the street, it would break its own legs, right? And so that's a really interesting feature. So I have to stop because we're out of time, but I want you guys to think about these puzzle pieces, and we'll come back to it on Thursday.